Made in 10.
I didn't have it. So now I have. No, that was my old, that was my other backpack. That was my backpack from work. This is my own personal backpack. What would have provided you with my backpack?
Hey Charles, how's it going? Look forward to the week when you're living.
Yes.
All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. All right. So week 10. So yeah, we're quickly approaching Thanksgiving. So next time I see you guys, it's going to be November. All right, and so announcements. So remember, project is due this Sunday, so it's going to be due October 30th, 1:59 p.m. I've definitely been talking to a lot of people this week about the projects, and so I know you guys are working on it this week. I'm going to try. I know people are probably working on it over the weekend, so I'm going to try to be as available as I can. I do have some friends coming from out of town, and so I don't know how often I can be at my email. But I will be available all day tomorrow. So, if you have your questions, please try to get them to me by tomorrow. If you email me over the weekend, I'll try my best to get back to you, but I don't know how often I can do that. So, but if you email me tomorrow, then I will probably get back to you within, hopefully like 20, 10, 20 minutes. And so I've been trying to be good with that this week. Okay? All right. And so, for today's lecture, I have to apologize a little bit. So I am feeling kind of a little bit sore throat. That's why I'm kind of wearing the mask again. And so I might be coughing, or my voice might sound a little bit hoarse today. So I apologize. So if you're having trouble listening to me, or trying to hear what I'm saying, just go ahead and let me know. If you can say, hey, what'd you say? It's like, can you repeat that? And so I'm always happy to do that. So please stop me if I'm either going too fast, or if my voice is too hoarse. Okay. All right. And so in terms of the lecture, where we kind of stopped in the middle of an example, just like last time, I guess. And so we're going to finish up that example. That's the last example I have for trusses. I have just kind of a couple more small points to make with that. And then we're going to move on to beams after that. Okay. So we're trudging right along with the direct stiffness stuff. All right. And so that's everything I have to say. And so are there any questions I can answer before we get started for today? Oh. Can't tell. Is that someone speaking outside the classroom, or is that someone on Zoom? That's outside the classroom. Okay. Okay. Sometimes the speakers, I don't know how exactly they're doing. So I can't tell if they're if it's the speakers or someone outside. Okay. So this is the example we were doing. And so we had a simple 2-truss system. And so we had two elements here, element A, element B. And just like normal, we're interested in computing the nodal displacements for this truss bar. Okay. Okay, and so we're going to go through our entire finite element process, same as we did before. And so we're going to be computing the element stiffness matrices. We're going to be assembling them into a global stiffness system, and then we're going to be solving it from there. Okay. All right, and so where we left off was computing these element stiffness matrices, and the main point I wanted to make before we left last time was to be careful about the angles that you put into the system. Okay, because when we define the angles, or when we plug that into our element stiffness matrix for a 2D truss, the assumption is that the angle that we plug in is the angle that that element makes with the positive x-axis. Okay? And so the trick that I told you guys about last time was to take your element, draw an arrow from the lower numbered node to the higher numbered node. Okay, that's going to be your element vector, and then from there compute what angle you would need to rotate from the positive x-axis in order to get that vector. Okay. Excuse me. And so for element A, even though in the figure here we can see that element A makes a 30-degree angle with respect to element B, okay, the arrow that points from node 1 to node 2 is actually, we'd actually have to rotate by 150 degrees from there. Okay. All right. And so, we would have that rotation. And so the angle we plug in is 150. And so if we plug in an angle 150, cosine of 150 degrees is a minus √3/2, and sine of 150 is a positive 1/2. Okay, and so we plug all that in. We plug in the values for AE/L. We get 2.5 times 10⁵, and then we get the following system. Okay, and then we did the same thing for element B. So for element B, even though it's a horizontal element, in order to get that exact angle, you would actually have to rotate 180 degrees, because the arrow from the lower numbered node to the higher node points to the left. And so that would be 180 degrees of rotation. And so we plug in 180 degrees, we get cosine of 180 is -1, sine of 180 is 0. And so we plug that in and we get the following element stiffness matrix. Okay. Right. And so, when you're computing these element stiffness matrices, you want to be careful about the angle that you plug in, because it may not be obvious from the figure. Okay. Okay. And so now that we have both element stiffness matrices, we are ready for assembly. So for this geometry here, we have 3 nodes. And so we have 3 nodes, then our global stiffness system is going to be 6 by 6. Okay. So let me go ahead and do that. So we're going to have D1X, D1Y, D2X, D2Y, D3X, D3Y. Okay. Now on the left side here, we're going to have F1X, F1Y, F2X, F2Y, F3X, F3Y. And of course, on the right here, we have D1X, D1Y, D2X, D2Y, 3X, D3. Okay. All right, so there's our global system. And so it has the X and Y deformations for all 3 of our nodes. Okay, so that's going to be 6 rows and 6 columns overall. And now we're going to be inserting the values into this system. Okay. All right. Oh, actually, let me do one thing first. And so, because we have a factor of 10 to the 5th on the outside there, I'm going to put a 10 to the 5th there. Okay, so that's just going to make it a bit easier for us when we plug in. Okay. All right, so let's start with element A. So element A here, we know is connected to nodes 1 and 2. And so that means we're going to block off the 1 and 2, node 1 and 2 rows and columns of the global stiffness system. Okay. Okay. And so that's going to be that segment there. Okay. All right. I'm not going to fill in the values just yet because this actually gets a little bit messy because we have √3s over 2s. And so I'm just going to show you what sections they're going to be in. Okay. All right, so now let's do element B. So element B here is connected to nodes 1 and 3. Okay. And so we're going to block off those sections. And so, unlike element A, for element A, we get kind of a nice big contiguous block for it all 16 values. For element B, we're going to have to split it up. Okay. So we're going to have this section for D1X, D1Y. And we have the cross sections for D1X, D1Y, and D3X, D3Y. We have the D3X, D3Y, D3X, D3Y. Okay. All right, so those are the sections of the global stiffness system that we're going to plug in our values. Okay. All right, so let's go ahead and start plugging in. And because this system is not, the numbers are not going to be that nice. I'm not going to, do the overlap and do pluses or whatever. So the global stiffness system I'm going to write down is going to be the result of, already adding together the parts that overlap. And really, there's only one section where it overlaps, which is this one up here. Okay. All right, so in the top left here, we have 6.875. We have minus 1.08, minus 1.08. 625. I apologize for the lack of narration, but these numbers are a little bit not very nice, and so I had to focus to make sure I put them in the right places. Okay. All right. So that is our global system. Okay. So we entered all the entries from element A, and really all the complications are coming from element A. Element B kind of fills everything. And as always, for sections of the global stiffness system which are not boxed, we're just going to input zeros in those locations. Okay. All right, and so that is assembly. Next thing we're going to do is the boundary conditions. And as always, we're going to start with the supports. Okay, and so we're going to start with the places where we are constraining our geometry. And then from there, we're going to put in our loads, which we just have one in this case. Okay. All right, so first thing that we notice from the geometry is that we have a fixed constraint or a fixed support at node 2. Okay. And so this is going to tell us that d2x is equal to d2y is equal to f2x, f2y, all of that's going to equal to 0. Okay, and so we're going to go to those rows in the global stiffness system. Okay, so it's going to be the third row and the fourth row, or f2x, f2y, or d2x, d2y. Okay. And we're going to replace these with the appropriate values. For some reason, my eraser is not really working. Kind of comical. Okay. Anyway, you guys know what we have to do. So it looks basically just like that. Okay. Oh, well, good enough. Okay. All right. And so that is that's our fixed support. Okay. And so that's going to be knocking out rows 3 and 4. Next boundary condition that we have, remember, is a roller support. And so the roller support, this was acting on node 3. Okay. And remember, the roller support's a bit different than the fixed support, because the roller support is only going to constrain one direction of the deformation. Okay. And so we go back up to the figure here. We can see that the roller here is vertical. Okay. And so what this is going to do is that it's going to prevent any deformations in the x direction. So any deformation that's going in the x and y direction, that's going to be set equal to 0. Okay. And so what this means is that d3x is equal to f3x is equal to 0. Okay. So this is different. And so, normally with the fixed support, we knock out both components of the deformation, but this time we're only going to knock out one of them. Okay. So if we go to f3x right here, we're going to change this row just like we did the row above it, but we're not going to change the f3y row. Okay. Like I'm playing a scratcher on my, scratching off a lottery card on my iPad, trying to erase those values. Okay, and so applying our boundary conditions, we get the following system. Okay, although we're not done yet, and so remember we also have our load. And so our load in this case is a minus 25,000 pounds applied in y direction or node 1. Okay, and so this means that F1y is equal to minus 25,000. Okay. Okay. And of course, this means that everything else that we haven't specified yet their values are going to be 0. Okay. All right, enough fighting with that eraser. Okay, and so that's the system that we have after we have applied our boundary conditions. Okay. Any questions on how we obtain this result here? Okay. All right, and so, at this point, usually we're ready to solve. And so we've applied our boundary conditions and we can go ahead and solve it. There's one problem with this system. And so let me go ahead and highlight it. I'm going to use rainbow sparkles to highlight it. Okay, and so if you look at the section that's highlighted in rainbow sparkles, you'll notice that everything in that row, everything in that D3Y row, and everything in that D3Y column are all zeros. Okay, and so if you try to pop this matrix into MATLAB, when you have a row and column that's completely zeros, MATLAB is going to give you an error. Okay? And so it's going to tell you that it's this is not possible, and so it's going to say that you can't solve this matrix. Okay, and so when you have a row and column that's completely all zeros, the system won't solve. So if you try to plug this system in here into MATLAB, it's going to tell you that it's not going to have a good solution. Okay. And so in order to fix this, in order to make it so that you actually can solve the system, what you need to do is you need to go to that row and column and you need to put a 1 on the diagonal. Okay. So we're going to go here and put a 1 right here. And so we effectively turn it into a fixed support, even though we started with the roller support. What this is telling us, this kind of goes beyond just kind of a mild inconvenience. Okay, what this is telling us is that if this structure is comprised of just truss elements, okay, then if we put a roller support there, that it's actually going to be unstable, and so it's not going to be able to sustain any kind of or sustain this kind of deformation rate. Okay, and so what that means basically is that if you have a row and column of all zeros, then your system is going to be basically statically unstable. Okay, and so think about it too. So if you can kind of imagine this happening in real life. So let's say you have a couple popsicle sticks and you have a pin support on two sides. Okay, but on the one side you just have a roller. Okay, if you pull down on this, or even just by the act of gravity, what's going to happen here? Right? Because the thing's only a roller, then that thing is going to start to move down, right? And so in other words, it can't sustain this configuration in its current state, right? And so if you have a row and column of all zeros, that's basically what it's telling you. Right? And so actually, the real answer is that if you do get a situation where the rows and columns are all 0, and you basically have a busted system. And so, you need to kind of go back and see, can this actually happen? And is there kind of a better configuration for this? Okay. But the temporary fix, and so just to make sure that you can actually solve the system, what you can do is you can just put a 1 on the diagonal. Okay. And so what that effectively does is that it transforms it from a roller support to a pin support or a fixed support, just for the sake of solving the system. Okay. Right. So unfortunately, the way I've kind of restructured this class, this is kind of an unsatisfying conclusion to this, because roller supports are something that's used quite a bit in real FBA, right? We did it in activity 4 when we did the displacement condition on the road, right? And so this is used. It's just that because we're kind of stopping after beams, you're not really going to get a chance to see the roller supports really take a good effect. Because in order to see roller supports in kind of their glory, we need to go to frame elements. But frame elements, I've tried it a couple of times. I've even tried it with my grad students in 541, and it is universally disliked. It's like, I don't think anyone enjoys doing the frame section, even myself. And so it's a little bit too much work. But I did want to cover it here just to let you know that roller supports do exist. You can constrain just specific directions. It's just that for a truss element or a 2D truss element, it doesn't really quite work out. You're going to end up with unstable situations like this more often than not. But it is interesting to kind of see. All right, and so if you do, I'm going to post the next homework assignment pretty soon. And so if you do come across a situation where you do have a roller support and you have a row of all zeros and a column of all zeros, the way you fix it is you just put a 1 on the die. Okay. All right, any questions on that? Okay. All right, and so if you do that, we can go ahead and solve this in MATLAB. And so if we solve this in MATLAB, so we solve this in MATLAB, what we get is d1x is equal to minus 0.0862 inches. d1y is minus 0.549 inches. d2x and d2y are 0 because that's the fixed support. And d3x and d3y are also 0, because we've turned node 3 into a fixed support as well. Okay. Right, and so that is the last example for trusses. There's one more point that I do want to make, and it kind of leads into kind of a bigger point with ANSYS 2, and that is how to leverage symmetry. Okay. And so symmetry is a great tool in finite elements, and I'll show you how to do it with trusses here, just because it's fairly simple. But you can actually use symmetry quite a lot, in other situations too, and even in ANSYS. And so actually, if you haven't really started your simulations in ANSYS and you've chosen a particular geometry, you can actually use symmetry in that case. And there's a way to do it in ANSYS in kind of a very kind of clever way. But let's define symmetry first. So when I talk about symmetry, what I mean is that you have kind of the exact same. If you kind of put a mirror in the middle of a part, you're going to see the exact same part on the left and right of that mirror. Okay. And so if we draw a line in our geometry and we see kind of the same thing on both sides, that means we have symmetry in that geometry. Okay. Okay. And so, we can see this in a truss, like the following. So let's say that we have the following truss. Okay. Right, and so we have a 4-element system, 5 nodes, and they're all connected down to a single point. Okay. If we were to draw a line on this, it's like that, okay? And we look to the left of the line, we look to the right of the line, it's like we're looking at mirror images, okay? And so this would be a situation where we can apply symmetry to simplify our finite elements, okay? So this line right here is often called either the line of symmetry, or if you're in 3D, it could be a plane of symmetry. And so symmetry is great because basically what we could say is that if we look across this line of symmetry, we have a finite element problem on our left, we have a finite element problem on our right, and those two problems on the left and right are the exact same problem. Okay? And so if we have the exact same problem, there's really no sense in solving it twice. And so, why don't we just solve it once? And so if we just solve it on one half, then we just copy that exact same solution onto the other half. Okay. All right, and so instead of solving that problem there, which has 4 elements and 5 nodes, even though 4 of the nodes are fixed, what we can do is we can solve this instead. So okay. And so we're just going to solve one of these problems. Hopefully that looks familiar because that's the problem that we literally just did. Okay. And then we can solve this one instead. So symmetry is great because it saves you a lot of, first of all, it saves you a lot of work. But second of all, if you're applying symmetry in an ANSYS context, it's going to save you a lot of cost as well. Okay. Probably one thing you guys are running into for the project is that, you want to add more elements, you want to add more accuracy, but it's taking your computer longer to do it. And, eventually you're going to run up to the numerical limits on the student license. Okay. Imagine that if you only had to run a simulation on just half your geometry, right? If you run on half the geometry, then, you have half the amount of space. And so you can crank up the number of elements by double, okay? And you get that much more accuracy on kind of a smaller space. And so symmetry, when you see it and when you can apply it in your jobs is really, really clutch. I think, probably the number one, cost saver that you can do, okay? Okay. I don't care how big a whiz you are with meshing in terms of, how do you refine in certain areas, how many little tricks that you do with meshing, okay? You're not going to beat symmetry. And so symmetry is literally a 1/2 reduction in the amount of in the amount of space that you have to simulate. And so, you're not beating that no matter how much of a whiz you think you are with meshing. So if you can apply symmetry to your problem, that's a huge plus. Okay. All right, and so the only thing that you have to kind of be careful of is that not only do you have to have symmetry in the geometry, you also have to have symmetry in the boundary conditions as well. And so it's not going to work if you don't have that that symmetry. Okay, I'll give you one example here. And so let's say that we have a couple springs and they're attached like this. Okay. Let's say that this point right here is fixed. Okay. We'll say both of these are identical springs, and so they have the exact same material properties. Okay. But if we have a situation where if we're pulling on one spring, so let's say we're pulling the spring on the right in tension, but we're compressing the other spring, on the other side, we can't apply symmetry here because the boundary conditions are different. Okay, and so even though the geometry is the same, the material properties are the same, we can't apply symmetry here. Okay? And so that's one thing you have to be careful of, when you're applying symmetry. Because obviously, if the loading is different on both sides, they're going to have different responses. And so you want to make sure that you account for that. Okay. Another thing that you have to do is that it's a bit more than just slicing your geometry in half and then calling it a day. And so one thing that you have to do is that wherever you make a symmetry cut, and so wherever you kind of slice your geometry, you have to apply what's called a symmetry boundary condition. Okay. Okay. And so when I call it a symmetry boundary condition, it sounds very fancy, but it's actually not. And the reason for it is it makes a lot of sense too. Okay. And so even though you're making a symmetry cut, you're basically making a cut in your geometry. You're not physically actually making a cut in your geometry. So you're not taking your your bucket or something and cutting it in half and say I'm simulating that, right? You're still simulating the whole bucket, but you're only just doing half. Okay. And so you want to make sure that when you do make that cut and you apply your loading, then you don't have any kind of unphysical behavior. Okay. And kind of the main unphysical behavior that you have when you make a symmetry cut is whenever you have deformations that go into the plane of symmetry. Okay. Okay. All right, so let me take let me do a 3D example just so you can see. So let's say that we have a box, right? The box is very symmetrical. Let's say that we make a symmetry cut here. So if we look at this geometry here, it's going to look like this. Okay. Where the highlighted surface here is kind of where we made our cut. Okay. So let's say that our box is loaded in the following way. And we're going to apply loads here. And so let's say that we have a load that's pushing on this edge right here. And we have a load that's pushing on that edge right there. We have a load pushing on this corner like that. Oh, that's being pushed on that corner like that. So our cube here is kind of being squished from all sides. Okay? And so, of course, when we cut this in half, we're going to apply those boundary conditions too. Okay. And so when we apply the boundary conditions on just the left side of the box, we have that there. Okay. But, if we were to just kind of simulate this as it is, right? You can kind of tell that what's going to happen if we kind of push this box from the outside, this edge of the box is going to want to deform to the right. Okay. Use a different color for that actually. So if we were to just do this analysis on that half of the geometry, that's what would happen. And so we would apply the two loads that didn't get cut off, and then the box is going to want to tilt in that direction, okay? Like a leaning tower of box. But obviously, that's not going to happen in reality because, if we look back at the original box, the thing that prevents deformation in that direction is the other half of the box. Right? And so you want to make sure that when you make a symmetry cut like this, you prevent something like that from happening. Okay. And so to prevent that, we add our symmetry boundary condition, which is nothing more than just a roller support. Okay. So we add roller supports. On the symmetry cut plane. To prevent So we add those roller supports to make sure that deformation doesn't happen in that direction. Okay. And so this is another reason I introduced the roller, so that if you do want to apply symmetry, if you want to make any last minute changes to your midterm project, because I know for sure one of them can apply symmetry, or it depends how you load it, I guess. You can do that. You just have to make sure that you add the rollers. Okay. And of course, after the midterm project, I'll give you guys a week break so that we'll have a week break from ANSYS, and then after that we'll start talking about the final project. You can apply symmetry on that as well if you have a geometry that can do symmetry. Okay. And so that's symmetry. And so you could apply that in ANSYS, but you can also apply it to these truss problems as well. Any questions on that? Okay. All right, and so that's it for trusses. And so it took us almost 4 lectures of stuff to do it, but we finally got through trusses. Okay. All right, and so there's one more topic that I want to go over in direct stiffness, just because I think it kind of completes kind of a nice picture, and that's the beam equations. Okay. All right. Let's talk beam equations. Okay. All right, so up to this point, we've kind of gone over two of the direct stiffness elements. So we've gone over springs and we've gone over trusses, okay? And really, those two elements kind of behave more or less the same way. So they can just be compressed or they can be stretched, okay? But as you know, when you have a structural member, even a slender one, you can have deformations that go in different directions, okay? And so the beam element is really designed to kind of give us ways to compute deformations that are not compression or tension. Okay? In particular, beam elements are going to let you model transverse deformation, which is deformation that's perpendicular to the element, as well as rotation. All right, so let's go ahead and draw beam element. So the shape of the beam element is going to be, the same. And so we're talking about kind of a long, slender element here. Okay. And so up to this point, we've only covered truss elements that can deform this way. Okay. So truss elements can only compress and lengthen. But for beam elements, we're going to look at something else. And so for beam elements, first of all, we have transverse deformation. First of all, let me call this node 1, node 2. Okay. And so we're going to consider deformations that are perpendicular to the element itself. Okay, so that's what we call transverse deformations. As well as rotations. And so our rotation is going to be theta 1 and theta 2. Okay. And so rotation is not really a deformation. And so it doesn't mean that the point there is moving. But all the rotation basically tells us is the change in orientation of the beam at those locations. Okay. And so this is kind of a big shift. And so, we're not, we're just strictly in a 1D case here. So, we're not looking at beams pointed in random directions. But already in a 1D case here, we are up to 4 degrees of freedom or 4 unknowns per element. Okay. Okay. And so that means, if we have 4 unknowns per element, that means our element stiffness matrix is going to be 4 by 4. Okay. So beam problems are just naturally going to be a lot more difficult than truss ones because their element stiffness matrices are a lot larger. Okay. Okay. All right. Any questions on beam so far? All right. Okay, so now that we know what beams are and compared to trusses, what they represent, let's take a look at what the element stiffness matrix is going to be. So like I mentioned, the element stiffness matrix for our beam is going to be 4 by 4. Okay. And remember, the element stiffness matrix relates the nodal displacements or nodal deformations to the nodal forcings. Okay. And so our 4 nodal deformations here are going to be D1y, theta 1, D2y, theta 2. Okay. And this is going to be equal to our nodal forcing. So here's where things are going to be a bit different too. Okay. And so for the deformation rows, so the D1y and D2y, we're going to have a normal force there. And so we have a F1y, F2y. Okay. But for the rows that have the rotations are given in units of radians, which is not a real unit. Okay. And so kind of the nodal forcing that causes that rotation is going to be a nodal moment. Okay. And so we're going to call this M1, M2, or M1, M2. These are the net moments applied at the nodes. And so our element stiffness matrix has to relate these all of these quantities here. All right, and so I'm going to skip the derivation. And so if you're interested in the derivation of the beam element stiffness matrix, I do have it in the notes in pretty decent detail. But basically, the upshot is we're going to use the Euler-Bernoulli beam equations and then kind of put them into a linear algebra context. So that gives us 4 equations of 4 knowns. Okay. And so if you're interested, I definitely recommend that you check it out. But I'm just going to go ahead and skip towards the result. And so the result is that we're going to have E, which is the Young's modulus, multiplied by I being the moment of inertia of the beam cross section, divided by L cubed, where L is the length of the element. Okay. It's going to multiply by this 4 by 4 matrix. And so we have 12, 6L, minus 12, 6L, 6L, 4L squared, minus 6L, 2L squared, minus 12, minus 6L, 12, 6L, 6L, 2L squared, minus 6L, and 4L squared. Okay. And so, again, we're just looking at 1D beams right now. And so we don't have any rotation angles yet. Well, actually, I don't think we're going to do them at all. But, you can see here that we have quite a few, things to plug in. Okay. And so 16 values. And so you have a 4 by 4 element stiffness matrix. You have 16 computations you have to run. Oh, let me label stuff because I haven't labeled stuff yet. So E here is the Young's modulus. Right here is the moment of inertia. L here is the element. All right, so those are all properties that will be given to you usually in a problem, and then you just have to plug it. In. Okay. So before we jump into example, I do want to kind of go over the different supports, and we're going to introduce a new support here as well, because now that we have an angular rotation here, how our supports kind of interact with that and how it constrains that is going to change just a little bit. Okay. All right, and so I'm going to write this the three constraints here just in general. Okay, so even though I know for a beam we're not considering deformations in the x direction, but I'm going to show it to you anyway. Just so that you can just have it for your reference. Okay. So number one is a fixed support. So we're going to change the definition for this just a little bit, because for trusses, it didn't really matter because we didn't have any rotational deformation. And so we were actually using a pin support, and we were calling it a fixed support because it kind of played the same role. But in reality, a fixed support kind of looks like the following. And so, let's say that you have your beam. The beam is going to be inserted kind of directly into a wall or directly into kind of a really hard surface. Okay. And so in this situation right here, all three deformations are going to be set to 0. So deformation in the axial direction, deformation in the transverse direction, as well as the rotation are all going to be 0. So we have d1x, d1y, and theta 1. All of these are going to equal to 0. Okay. Or, let's say this is the x direction, this is the y direction, and this is node 1 here on the left. Okay. So I'm kind of redefining fixed support just because before it didn't really matter, but now that we have the rotational component here, I want to kind of differentiate that. If you have a fixed support, which kind of looks like the following, then the rotation is going to be set to 0 as well. Okay, next we have the pin support, and so this is the one that we've been calling fixed support all this time. And so it looks something like this, okay, where we have the part of our structure that's literally pin, okay, and that pin is assumed to be kind of on a rotating part. And so when you have a pin support like this, the deformation components are set to 0. And so we have d1x, d1y. Both of these are going to be equal to 0. But there's going to be no constraints on the rotation. And so, because you kind of have a rolling pin there, then that beam is kind of free to rotate. It can't move, it can't translate at all, but it can kind of rotate up and down. Okay. And so the way that we define that is that we set theta 1 is equal to 3. Okay. And so just like we did in kind of the first example we did today, if you were to have a pin support like this and you're looking at the row regarding the rotational displacement, you would just leave it as it is. And so you wouldn't change it at all. Finally, we have the rower support. So for the rower support, I'm going to go ahead and draw the beam here. So the rower support would look something like this. And so in this case, the roller is on kind of a horizontal ground. Okay. So since the roller is on horizontal ground here, it's going to prevent deformation in the y direction. So we're going to say d1y is equal to 0. But the support here is free to roll in the x direction and is free to rotate as well because it's a pinned roller. Okay. So those are the three types of supports that we are mostly going to be rolling with. So we have the fixed support. The fixed support is going to fix all three deformations. We have the pin support, which is going to just fix the x and y deformations, and we have the roller support, which is just going to fix one direction of the deformations. Okay. All right. Any questions on this before we jump into an example? Yep. Yeah, so theta 1 is free because we have basically a pin right here. And so the roller is pinned to the structure. Yeah. Yeah, so it's like it can rotate around that, I think. It's interesting, I can't believe in this semester also we were like literally dying in here because it was like 110 degrees outside and the AC was off, and now it's freaking cold and my nose won't stop running. Crazy semesters. Okay, all right, so let's do an example to kind of show or to illustrate kind of these concepts. Okay. All right, so we're going to do a beam problem, and so our geometry here is going to be a beam, and so of course that's going to change up the element stiffness matrices that we use, but our process is still going to be the same. So we're going to write out the element stiffness matrices. We're going to assemble it into a single global system. We're going to apply our boundary conditions, and we're going to solve it. Okay, so our process is the same. It's just that the element stiffness matrix is different. Okay, so let's consider the following beam. I'm going to split this beam into two. Okay, so the beam on the left I'll call beam A. The beam on the right I'll call beam B. Okay. We'll say that both beams here have a length of L. Of course, on the left right here at node 1, beam A is going to be fixed into the wall. And on the right here at node 3, beam B is going to be pinned. Okay. And node 2 at the middle, we're going to have a single load going vertically downwards, or P. Okay. In addition to that, we're going to have a torque that's being applied on node 2. We'll call that T. Okay, so T here is a torque applied on node 2. Okay. All right, and so for this problem, we're going to assume that the Young's modulus and the moment of inertia are known. In fact, we're going to assume that it's the same for both elements. And we're going to ignore any axial displacements. And so we're going to assume that these are pure beams. And so we're not going to have any, compression or tension. And what we want to do is we want to, well, in this case, I don't have any numbers here. And so we can't fully solve this problem. But what we can do is we can basically assemble our global linear system and apply our boundary conditions. Okay. All right, so let's go ahead and go through the process here. I run out of time, but we'll see. Okay. Okay, so this example here, of course, we're not going to be plugging anything in because we don't have any values. But this example here is kind of to illustrate what to do, for the different types of boundary conditions that we have. Okay. All right, so let's start with element A. So element A is a standard beam. So say Ka. This is equal to E times I, the Young's modulus multiplied by the moment of inertia divided by L cubed. Okay. And this is going to be multiplied by our beam element stiffness matrix. So 12, 6L minus 12, 6L. So on and so forth. Okay, so that's our standard beam element stiffness matrix. And of course, you would plug in, plug in the values if you had them. And the other thing we have to do is we have to indicate which nodes that this is connected to. So this is U1Y, theta 1, U2Y, theta 2. Okay. Okay, let's do the same for element B. And so we have KB is equal to EI over L cubed. It's going to be the exact same thing. So 12, 6L minus 12. Okay. So same element stiffness matrix, but our nodes are going to be different here. And so element B is connected to nodes 2 and 3. And so this is going to be, I'm sorry, I'm using U again. So it should be D1Y, D2Y for the element A. And for element B, it's going to be D2Y, theta 2, D3Y, theta 3. Okay. All right, so fairly straightforward. And so, not too much to say there, just because we're not plugging in for that. Okay. And so our next step here is going to be assembly. I guess before we get that, and I'll give kind of people a chance to, if you're still writing stuff down. Any questions on this? Okay. All right, and so let's go ahead and assemble. And so because we have 3 nodes here and we have 2 degrees of freedom per node, our element stiffness matrix is going to, our global stiffness matrix is going to be 6 by 6. Okay. D1Y, theta 1, D2Y, theta 2, Y. All those are equal to the nodal forcing terms. Okay. So F1Y, M1, F2Y, M2, F3Y, M3. Okay. So just like we did before, we're gonna mark off the element stiffness matrices, okay? And so element A is gonna be nodes 1 and 2. And so let me go ahead and box those rows and columns, okay? And element B is gonna be nodes 2 and 3. So we have just like that, okay? So pretty straightforward here. So a pretty straightforward overlap. All right, and so if you were to fill in the values here, let's do that really quick. So of course we have EI over L cubed out in front. Oh, 6L, 12, 6L. And of course, on the overlap, we have 12 plus 12 here, which is 24. We have minus 6L plus 6L, so that's going to be 0. Minus 6L plus 6L is 0. And then 4L squared plus 4L squared, which is 8L squared. And everything else is more or less the same. All right, so pretty standard assembly. It's just that, probably the first couple of times you do it, it's going to be a little bit weird because you have all these L's and stuff floating around. But more or less the same process. Okay. And then for everything else, of course, that's not boxed, you just put a 0, just like that. Okay. Right. And so the final thing that we'll do today is we're going to apply our boundary conditions. Okay. And so our boundary condition is that we have a fixed support at node 1. So this tells us that U or D1Y and theta 1 are equal to 0. Okay. So that means these two rows here. Okay. And our other boundary condition here, our other constraint is a pin support at node 3. And so that means that only the D3Y row is going to be equal to 0. Okay. And so we're going to leave the theta 3 row alone. So we're not going to find any boundary conditions there. Okay. All right, let's see if the eraser makes me know. Understand why it's taking so long. Okay, so for the first 2 rows, we're going to have something that looks like that. Okay. And then for the last two, and for the D3Y row, look like this. And so just like we normally do, we're going to put zeros on every off diagonal and a 0 on the diagonal. Okay. And then on the right-hand side forcing vector, we're going to put zeros in those rows as well. Okay. And then last thing we need to apply here are just the loads. And so we have a load of P, I believe that's what we called it. Okay. In the negative direction. And so this F3, F2Y here is going to be minus P. Okay. And then instead of M2 right here, we're going to have our torque here, which is T. Okay, so both of those are being applied on node P. And of course, M3 right here, there's no load being applied to it. And so we're just going to sub in a 0 for that. Improvising with the Maggie iPad. Right, and so that's basically how you do it. And so when you're doing beam problems, you have to pay a little bit more attention to the supports or the constraints because they can be quite different. And so make sure you kind of pay attention to that and only knock out the rows that are appropriate. All right, any final questions on this before we wrap it up for the week? Yeah. Yeah. Yeah, I think I might have messed some. I missed a negative here, and I think there should be a negative. There is a negative here as well. Yeah, I missed these two negatives. I realized that as I was making. Yeah, and so when this block right here overlaps with this block, the negatives from the top one kind of cancel out with the positive ones. Yeah, I just missed a couple negatives as I was writing, but yeah, sorry about that. All right, any questions? Any more questions on this? Okay, all right, so that's all we got for today. So thank you guys for coming today. Remember, the project is due Sunday, and so if you have any questions on it, go ahead and shoot me an email. I'll try to be as responsive as I can over the next 3 days, just so you can get all your questions answered and make sure you turn in on time. All right, so thank you guys for coming today. I would say have a good weekend, but I know you guys could be working on the project this weekend, so I'm not going to say that, but I will see you guys next week, and hope you guys have a good Halloween too. Oh yeah, sure.
Are you like taking the classes? Yeah, and I know that I think we're only allotted about 28 units to take.
Yeah.
I'm a little not pretty as well. Okay, one of my classes in circuits, and I know that class historically has a high fail rate for mechanicals here.
Yeah.
I'm afraid that if I fail it, I won't be enough to retake it because I'm using the last of it to just retake 2 classes. Is there any way to fill?
And then what those ones?